Hello, this is the second part of the review series for the final exam. In this video, we will be doing linked lists and stacks and queues to finish off the rest of the course, and I wanted to separate this out since these are the two topics that are for sure going to appear on the final exam. So the first of which we talked about were linked lists. And linked lists were essentially an alternate data structure that we proposed, which functions almost like an array, however, has some key differences. So if I have an array like this, where it contains 4 things, and my array contained 3, 5, 7, okay, we'll do 3 things since I drew it too small. The linked list equivalent would look something like this, where it would be 3, then 5, then 7, each stored in these elements, which are not adjacent in memory, but instead are linked together with these pointers, where each cell in this data structure contains the data, as does the array version, right? The array version contains the data in these cells, these elements, and then in the linked list we have a similar thing where we have these cells where the data is stored, but since they're not adjacent, we link them together with this pointer to where the next cell is so that we know where it is. Right, so this was our general idea of a linked list, is instead of storing things contiguously, that is adjacent to one another in memory, we store our data discontiguously, where everything is in its own self-contained bubble, but they're not necessarily right next to each other, and that's why we need the pointer. And the point of this data structure, as opposed to an array, was that it allows us a little bit more flexibility with interacting with it. So inserting things into the middle of the array, for example, is kind of difficult because everything is adjacent and it needs to stay that way. So if I wanted to put a 4 between this 5 and the 7, I would need to either find a way to move the 3 to the left or find a way to move the 5 and 7 to the right. There's just no easy way to do that, versus if I want to put a 4 in between here, I can simply just rearrange the pointers, right? So there's some flexibility in interacting with the middle of this linked list versus an array, and if we want to rearrange the components with anything other than a swap, then it becomes easier to do than with an array. And so we talked about some advantages and disadvantages. So we'll go over those again really quick. So we'll say arrays here on the left-hand side, and then linked lists on the right-hand side. And I'll denote neutral facts with just a dot, and then I'll give positives with a plus and negatives with a minus. So arrays are contiguous in memory, as we said. That means they're just next to each other. Whereas linked lists are discontiguous, meaning there's no connection between any two cells, any two nodes. They're just going to be anywhere in memory. They could be before each other, they could be after each other, and while we draw it left to right, there's no connection between any of our actual pieces of data, no direct connection at least. Okay, and because of that, it's very quick to access elements in an array. Whereas in a linked list, we have to traverse the list to access things. So if I have this example again earlier where I want to get the number 7, in an array, because everything is right next to each other, we can just jump from the beginning of the array 2 spots. We can calculate that with a simple expression where we just add however many memory units to the right 7 is from the start of the list. Everything is fixed. It's really easy to calculate. So, we just increment a value by something. Whereas in the linked list, there's no order to these things. While I'm drawing them left to right here, the addresses of this could be anything. They're totally arbitrary. So while, 3 and 5 could be at a higher memory location, 7 could be at the beginning of memory, and we have no relation between these two things. They're just completely random, and they change between different runs of the program, because remember that dynamically allocated memory on the heap is completely arbitrary. It's random, and we can't make any predictions about it. So I can't just automatically assume where 7 goes in memory relative to anything else. It's not always going to be like 4 blocks to the right of the 3. It might be before it, it might be after it, and the difference and the distance between those two things in memory might change. It's variable. But that's not the case with an array. So arrays are predictable in their layout and thus are very easy and quick to look up things. You just grab the 7 from the array and it's fine. But if I want to grab the 7 here, what I have to do is start at the head pointer, which we said is the pointer which represents the beginning of the linked list, and then we traverse it by following each pointer. So I go from 3 to 5 to 7, and then we work our way from the left to the right until we hit where we need to go. And this is still true in a doubly linked list, right? It's just you have the option to go right to left as well, but the problem still exists. You can't just jump to an arbitrary point in the linked list. You have to traverse it in some way by following the pointers. And so that means that on average, it is slower to access something in a linked list because of the way that it is oriented. However, an array, its main disadvantage is that it can run out of space, and we must resize if we need more space. Whereas in a linked list, we cannot run out of space unless the whole program runs out of space. If the heap is totally out of memory, then the linked list can't do anything, but you can't do anything in your program anyways. So this is an issue with a array, right? Because everything has to be adjacent. If I was, for example, implementing a dynamically allocated list, which adds things to the end every single time, and I want to add a 9 to each of these data structures, I can't just append a 9 to the end of the array, because the memory to the right of this array is not guaranteed to be safe to use. It might be another variable. There might be integers or booleans or floats or class objects which occupy the space adjacent to the array, and we need all of these to be right next to each other in order to still be an array. So we can't just put the 9 there. We can't go out of bounds this way either, right? We would have to allocate an entirely new array of size 4 somewhere else in memory, make a deep copy, if you remember what we did in class. So I'd have to, actually what would happen, right, is we would make an array like this. It would be 4 big. We would copy over the 3, 5, 7 individually, and then put the 9 there. And even if you take some shortcuts on this, it still doesn't really fix the problem, which is that whether we like it or not, we're going to have to make a second array and copy the contents of the first array to the second array before it's usable. Right, so the issue with this is that when you run out of space in an array, if you want to continue using it, you're going to have to make a deep copy, and deep copies are computationally expensive. They take time to do. You have to ask for the operating system to make you a new array, and then you have to copy everything over to that array, and that's slow. So we don't want to do that. And so when you're weighing these advantages and disadvantages in your actual practical programming applications, then consider whether you're going to encounter these things, right? If you know you're very rarely going to resize, and you might potentially never resize, then an array might be inappropriate, or it might be appropriate, because you don't have this disadvantage weighing it down, but you have the advantage that the accessing is fast. But if you know that you need to rearrange things really quickly and you're going to run out of space frequently, then maybe you opt to use a linked list even though you know the traversal is slow. And you might do this also if you know you don't need to traverse it very frequently, and your usage of your data structure doesn't involve looking things up frequently. Maybe you just constantly add and then print it at the end or something like that, right? So you need to weigh what it is you're trying to do with your data structure and then pick the appropriate one. And these are just two simple data structures. You will learn more in future classes, but it's always something you want to consider when you're picking these. Right, so we need to we have these advantages and disadvantages, but we need to consider in what cases they're applicable. Are they relevant to the algorithm that you're writing? So last one I think that was important was an array takes the exact amount of memory it needs, and a linked list takes slightly more, but a fairly negligible amount of memory. And that's just inherent to the way a linked list works versus an array. An array is going to contain just the elements. If I want to store 3, 5, and 7, this array contains nothing but the numbers 3, 5, and 7. But this linked list inherently needs to store things other than 3, 5, and 7 because of the way it works. It needs to store a pointer to the next one. While we didn't go into it in detail, we did bring up the fact that everything requires a memory allocation. That goes for pointers as well. They are data types which hold addresses. Addresses are 8 bytes, so the pointer takes up 8 bytes, which means that this extra part here on each node will take up an additional 8 bytes per node that is not present in the array because the array just stores what it needs to. So each node takes up slightly more memory than an individual element in an array. This becomes more negligible when the data type that you are storing in the node changes. In this case, we're storing integers, which are small, but you might store something like class object, right, which has many variable members, and it's going to take up a lot of memory space, at which point the 8 bytes is relatively small compared to the data that you're storing in there and isn't a huge deal. But that being said, it might add up. If there's 1,000 of these, right, and you're using roughly 3 kilobytes just to store the pointers, that's just a quick mental math. I think I'm right there. So just something to consider, right? Okay, so those are advantages and disadvantages of linked lists. Just to kind of refresh how a linked list works, a linked list is a data structure. An array is a data structure. A vector is a data structure. A stack and queue are both data structures. So a data structure is just a general term that means a place where you store data. And it's usually related data. So in our example before, all of our data were integers. And when you declare an array, you usually put, here's the type of my array. This is what it holds. If I make an integer array, it only holds integers. It won't hold anything else. It can't hold floats. It can't hold class objects. And so there were 3 major operations that we are concerned with for most data structures. This may differ depending on the data structure. It may have some more operations which are crucial to its function, and some of these might not be relevant, but generally the 3 that you're concerned with and that every data structure will have is insertion, deletion, and a search or a lookup. Let's call it search here. So insertion is when we put things into the data structure. We have to define how that works and how long it takes. Deletion is when we find an object and we remove it from the data structure. And then search is when we find an object in the data structure and either return a Boolean stating whether it is there or not, or return the object itself. It's not super relevant to a linked list, but it will be later as you do future data structures where there's extra information. Okay, so we talked about how to do these three basic data structure operations on a linked list. For the insertion, we remember that a linked list will always keep a head pointer, which just represents where the first node in the linked list is. When there's nothing in the linked list, this will point to null pointer because there's nothing in there, so there's no node for it to point to. However, as we insert nodes into the linked list, we will insert them at the head. So maybe we do an insert like 3 there, and then we might insert 5, and then we might insert 7 afterwards. And the end will simply be a null pointer. For each node that we have in our linked list, it will contain the data and then the pointer to the guy after it. So whenever we add something, say I wanted to add a new node containing 10 here, what we do is create the new node, we'll set the head if it's uninitialized. So notice when we introduced that 3 node, it was originally pointing to null pointer, but we replaced it with a real node. Every subsequent addition after that, where we put the 5, 7, and 10, the head is still pointing at 3, so it doesn't need to be updated again, but only when it's uninitialized, or at least pointing to null pointer. So I guess I should be careful there. It could be initialized to null pointer. Otherwise, what we want to do is go to the end of the data structure. So we want to traverse it, right? That's what we said we have to do every time we want to interact with the linked list, is we start at the head, we go from 3, then we go to 5, then we go to 7, which is the end of the linked list currently, before we insert the 10, and then we can insert the 10 there. So we update this 7 to point at the 10, and set the 10 to point to null pointer since it is the new end. So finally, we link the created node. And this is our general algorithm, right? These comments might be a few lines of code, but the idea is, right, create the node, find where to put it, which is at the end, then link it to that end by setting the pointer to that thing. Now, obviously, this is kind of an issue in terms of speed, because here, every single time we want to insert something, we have to begin our search at the head and then go bump, bump, bump right until we hit the end, right? And so notice that as the size of this list grows, the number of times we have to follow a pointer grows as well. If I have 100 nodes in my list and I want to add 101st node to my list, I have to follow 100 pointers until I end up at the right place. And that is going to get slower and slower the longer or the more data that we add to the linked list, which is its biggest disadvantage. However, we can mitigate this problem if we understand that the insertion works this way. In the basic implementation of a linked list, we are inserting data at the end of the linked list. Note that this is not always the way this works. Remember, we did a sorted linked list in our class during lecture. But if it's the default behavior where it goes to the end, we know we're going to need to go to the end every time. So what we might do to avoid having to traverse the whole list every single time is create a tail pointer, which represents the end of the linked list. At that point, our algorithm still works. We'll create the new node. So if I want to insert another new node here, like 12, we'll set the head if it's null, it's not. We'll go to the end. The nice thing about that is that we already have a way to get to the end. The tail tells us where the end is without the need to start at the head and go right until we hit it. So we can simply link that to the tail. We don't have to iterate through and traverse over everything. And then now this new element that we've introduced is the tail of the list because it's the last thing there. Right, so the tail pointer was something that we talked about, where as the head points to the beginning, the tail points to end. And it's ideal when you need to insert at the end frequently because it avoids the overhead from traversing the list. That is, we don't have to take the time to go through every single element, which is slow. It takes a while to get from the start to the end, right? We can just jump straight there. So at least mitigates some problems, although if we need to interact with the middle, it's still an issue, right? Which we might. We do for the delete and the lookup. Okay, so that's our insertion. General process. Then we went over lookup or search. And this one's relatively simple. We have our linked list like this. And it doesn't matter if we have a tail pointer here, so I'm just going to do a head pointer. Say I'm looking for the number 5. What I need to do is start at the first node, right, 3. Then we'll check if the element that we're looking for is in the node we're currently in. In this case, it's definitely not, right? So we'll move to the next one. And then we found it. So that's great. We would either return true or return the 5 that we found. Otherwise, if we're looking for something like the number 4, I understand that my linked list is sorted here, but that might not be always the case. So if we assume that this isn't sorted, we would go 3. We would say, well, that's not the 4, so we'll try the next one. That's not what we're looking for. It's not 4, so we try the next one. And that's also not 4. At which point we reach the end of the list, there's no more nodes left, and we say, okay, well, we didn't find it, and return either false or throw an exception, do something that represents that we didn't find what we're looking for. So that one's, I think, fairly simple. It's basically the same process as reaching the end of the list, but just at every step, we'll check if we found the thing that we're looking for by checking if the data matches. Deletion works much the same way. At least as a starting point. So what we do first is find the node to delete. Let's say we want to delete 5. Then we would first find where that node is. So we would start at the beginning. We would check, okay, is that the 5 we want to delete? No. And then we would go to the next one, and that is the one we want to delete. So we want to delete this 5. We'll call this pointer cur, the one we want to delete. And then note that if we didn't find it, it would be like the lookup where we returned false. We just wouldn't do anything. There's nothing to delete because we didn't find it. Okay, but let's say we want to delete this 5. What we do is traverse the list until we find it, and then we would delete it. However, if I just wrote delete cur, what it's going to do is kill this node right here. The issue with that is that this 3 pointer is still pointing to the 5. The pointer from the 3 node is still pointing to the 5. And the 5's pointer to the 7 is now gone. So what we've done is we've broken the link. The 3 is now a dangling reference. It's pointing to a deleted node that isn't helpful to us anymore. And the 7 has no more pointers left to it and is thus a memory leak. So anything to the right will memory leak, and the pointer directly to the left will be a dangling pointer. So we can't just delete cur immediately. We have to do something else. So the issue here is that after cur has been removed from the list, this 3 needs to be pointing to the 7 node so that the linked list we get afterwards is still valid, right? If we remove 5 from it, then the linked list will be 3 goes to 7 now, because 7 will be the one coming after 3, because 5 is no longer in the way. Right, so what we need to do is we need to update that pointer. And what we notice here is that that 3 is going to point to the next one after cur, right? However, the issue here is, even though we have this head pointer, that's not necessarily going to be the case. Right? So just to make this picture more clear, there could be any number of nodes before this 3. It doesn't necessarily have to be the head. And what that means is that if I want to set this 3 equal to the 7, I can't really do that if I am searching for the node with the 5 in it. So what we need to do is either stop one early. So what we could do is we could actually stop here at this 3 node and then use that one. Or the way we came up with in class was we simply keep a pointer to the previous one while we're traversing. And then at each point, as we move right, we move the cur and the previous right 1 pointer each time until we find the node that we want. In this case, we can now set things because the previous next can equal the current next, so that it points to that one, right? And then now it is safe to delete cur because the structure of the list is fine if the 5 is removed. So we can delete the 5 and everything's okay. So our deletion process was find the node we want to delete, keep a pointer to the last one, that way we don't accidentally break the structure of the list, and then we simply redirect it to point to the right place. Okay, so that's our deletion operation, and those were our 3 operations for a singly linked list. For a doubly linked list, our only difference between that and a singly linked list was that instead of just a pointer to the right node, to the next one afterwards, we also kept a pointer to the left. So that same linked list that we had before might be represented like this using a doubly linked list. This was really our only difference, was that it had a previous and next, and what this affects is that we need to set both the previous and the next whenever we do anything. Okay. So let's go over the 3 operations again. Insertion is almost identical to our singly linked list. So let's say we have just 2 nodes and we want to insert another one. So right now it looks like this. Then the next node should go to the end, so we will navigate to the end of the linked list, which we can either do, again, by starting at the head and working our way right. Nothing changes there, right? Otherwise, if we have a tail pointer, we can simply go right there. We will create the node that needs to be inserted. We will link it to the tail. However, now on top of that, we have one extra step, which is that we need to take this 7 and point it back to the 5. So we have one extra step of whatever the new node that we're inserting is needs to point backwards at the tail. And then, like we did in the singly linked list, we'll simply update the tail to point to here. Insertion really just has one extra line of code compared to the singly linked list node version, which is just we need to set the previous of the last guy that we're inserting. That's really it. It is that simple. It's almost identical. Lookup / search, I won't even do because it's exactly the same. If you want to look for something in a linked list, you start at the head, work your way right. Like we did here, right? We started this head, we kept a pointer and kept going to the right. But that doesn't change in a doubly linked list. The ability to go left doesn't affect the fact that we're still searching to the right. So there's no difference in lookup and search for a doubly linked list between a singly linked list. It is exactly the same. That means for deletion, our lookup will be exactly the same. We just need to address how the different pointers work. So if I have some arbitrary place in the list where this is somewhere in the middle, and then we have the 3, 5, and 7. And let's say again we want to delete the 7. What we would do is we would start at the beginning of the list, work our way right until we finally reach the node we want to delete. I'm sorry, did I say delete 7? I meant delete 5. So starting point is exactly the same. Find the node that you want to delete. Then afterwards, we can delete that node. Again, if we just naively immediately delete this, then it's going to be a problem because this 3 is pointing to this 5, which no longer exists. The 7 is also pointing to the 5, which no longer exists, and the structure of the pointers was not maintained. So we want to delete cur, but we need to do some things beforehand. And when we were deleting the singly linked list, we had to keep a previous pointer because this guy needed to point over here, right? When we're updating this one, the 3 will need to point to the 7, the 7 will need to point to the 3, since we're removing the 5 in between. However, we have the ability to go left now. That was our advantage of a doubly linked list, is it allows you to traverse both directions, and so there's no need to maintain a previous pointer. Instead, this node right here, we can say is the previous, or sorry, the cur's previous, right? Because it's the one that came before the cur node that we're deleting. And this guy right here would be the next one after the cur. And so what we want to happen is we need this 3 to point to over there, which means that the cur previous, its next one, the next one after the cur previous, the blue node, which I guess I should highlight if people are colorblind, is the next one after the blue node, this squiggly one, is cur next. Right, the next one after this node on the left is going to be this node now. This will redirect this pointer over to here. And vice versa, we want this 7 to point backwards to the 3. So the cur next previous will be the cur previous. So that will take the 7 and point it to here. The pointers coming out of the 5 don't matter because we're about to delete it, so we don't need to update them to anywhere. They're going to get removed anyways. After we update these pointers, the 3 is pointing to the right place, the 7 is pointing to the right place, we can then kill cur, we can delete it, and it's removed from the list, but the structure is still maintained because now, in its absence, 3 and 7 are pointing in the right places, right? And so that was how we did our deletion. In a way, it was easier than doing the singly linked deletion because we don't have to keep that additional previous pointer. We can go backwards. However, we needed to be careful with the way we did this, and so we use kind of like a substitution. Always, when you're solving computer science problems for the first time, draw it out, make sure you understand it. It's okay to highlight things or give things aliases, like variable names, call it A or B or C, whatever you like, right? And then work out the problem and then figure out how that applies to this problem. So here I've denoted them blue and green, but you could call them A and B. Just give it some sort of alias, some meaningful name. That's what you're supposed to do when you're programming, right? Okay, so this were our data structures for linked lists, their advantages and disadvantages and how they work. One last thing that we mentioned was the idea of a circularly linked list, and the only distinction there was that any ends don't point to null pointer, but instead point to the other side, so it wraps all the way around. In a singly linked list, this means that the tail points back to the head, and if it was a doubly linked list, which was circularly linked, then the head would also point back to the tail. So if this was doubly linked, this would go like that. And that was about it as far as our linked lists go. The last topic we talked about in class were stacks and queues. And we first talked about queues. But just to note, stacks and queues are data structures, and they might be built upon other data structures. In class, remember that we implemented each of these with an array and a linked list, so you have some option and some flexibility to implement these in different ways, but they are still data structures. They're just data structures built upon existing data structures. They're just more sophisticated data structures, I suppose we could say. The first one we did, which was fairly intuitive, was a queue. The queue is a, sorry, I should be careful. A queue is a FIFO data structure, which means first in, first out. And it functions similarly to a line. What we do is we keep a front and a back. And as we insert things into the queue, insertion was called on queuing. And it works like a line where anytime a new object is added, they're added to the back of the queue. If I wanted to on queue A and B, then A is at the front because they got there first, and then B is at the back. And if I on queue a third thing, C, then it goes at the back, and the new back of this queue is C. We can also remove from this data structure. We can dequeue from it. So these are essentially our insertion and deletion operations that we talked about earlier. And when we dequeue, we remove the first object, and the next one object becomes the front. So this is analogous to a line at a store where whenever the cashier asks for the next person is the person at the front of the line, and if you're getting into line for the first time, you go at the back and you wait your turn until you get there. So I think a first in, first out data structure is fairly intuitive. It works maybe the way you expect. And one of the other things we noted about this was that it is order preserving. Which means that if A, B, and C show up, they leave in the exact same order. Right? The order of arrival and the order of departure are exactly the same in this vanilla normal queue. It does not matter if I dequeued before C showed up. Right? If the cashier asks for the next person, they're still going to take the person at the front of the line, even if somebody shows up while they're doing so. Or before they do so, or after they do so, the next person is always the person at the front. and the person who shows up next will go to the back, so they have no effect on the people in the front, which means that the order will always be the same no matter what permutation of onQ and DQ you do, as long as they're valid. As far as applications of queues go, we can use them for things like lines of customers, making schedules of things. So if you want to make a to-do list, for example, you can say, I want to do this, and then I want to do this, and then I want to do this, and I want to do this in this order. And then as you DQ them, it will give you those tasks back. I'm saying this at a high level as just like a to-do list, but in actual computer science, a schedule might refer to programs. You might say, let this program execute first, and then this program, and then this program. So it's appropriate for scheduling things. Basically anywhere where you need an order. So if you want to keep track of things that are time dependent, like for example, you're doing a real-time application where you have frames, and like a video or a video game, then you might put those into a queue so that you process them in the exact same order that they show up. Right? If you're watching a movie, then you might have a queue of the frames. The order of frames in a movie needs to be exactly the same that the director put them in, or the editor put them in. Otherwise, the movie won't make sense. You can't just show random frames or permute them. Right? They have to be in the order in time. Right? So there's an order that's preserved. So if you're writing a video player, for example, application, that would be an appropriate place for a queue. The other data structure that we talked about were stacks. And while queues are FIFO data structures, stacks are either LIFO or FILO, depending on who you ask. And what this means is last in, first out. These were a little less intuitive, but actually very, very, very useful. So as a queue had a front and a back where we insert and remove from, a stack keeps only one variable, which is called the top. The top represents where the top of the stack is. Think of it like a stack of blocks or a stack of plates. When you do an insertion, which is called pushing, you put the block on the top of the stack. So if we want to put an A here, we'll create a frame, and that's where the top is. And if I want to insert again, I push a B, then I can't put it underneath the A, otherwise the tower will fall over. Instead, we put B at the top. So it's named a stack after a stack of plates. Whenever you remove or add one plate at a time, you do so from the top. So again, if I want to push an object, C, then we add it to the top, and that becomes new top. When we pop from the stack, we also remove from the top. If I was to pop from this stack, I would be popping the C, and the new top would be B. If I wanted to remove a single block from this tower, the one that I remove is the one on the top, because if I remove A or B, the whole stack falls over. It collapses. Right? And then we might push D here. And then D would go into the top of the stack. And then if I was to pop, I would pop D, right? So the thing about the stack is that it is not order preserving. That's not its intention. If I was to remove this pop, then the C would still be on the stack. And if I moved that pop down to here, then it would pop D first, then C, whereas before it removed C, then D. So notice here that the order that I do pushes and pops in actually matters and affects what gets out, because the last thing that I put in will be the next thing that comes out of the stack. Which means that it is not intended to keep any sort of order, unlike a queue. While we can use it to, for example, reverse things, if we push everything and then pop everything, it will reverse it. That's not the case if we have pops anywhere in between a push, then that's not going to be the same, right? So this won't pop DCBA. This will pop CD, and then presumably if we have pops down here, B and A. Instead, the point of a stack is that it keeps track of some history. And just to distinguish, like we did in lecture, this isn't history as in like a list of things. It's not like a ledger where you just write down this is what happened. It's not a diary where you just keep things down. That's more of like just saving something to a file, right? It keeps track of the order that history happened in. So we said that this might be appropriate for things like your web browser, where every time you click on a new page, it opens up that page and it adds it to the stack. And whenever you hit the back button, it pops from the stack and returns to the last one. So it keeps track of history in the exact order that you did it. Tree traversal is also done with a stack if you're doing specifically depth first search. If you remember that from mathematics, if you've taken discrete math yet, then if I had this A, B, C, D, and E nodes, the traversal for DFS is A, then B, then C, and once it hits the end, it backs up to B, and then goes to D. So it keeps some sort of history of where the last node that it visited was, and then backs up to that. If you're not familiar with DFS, no worries, you will learn about it at some point. But that's an example of where a stack might be appropriate. And then we had web browsers, right? Like if you click on a Wikipedia link on Google, and we click on that, then it adds a Wikipedia stack frame on top of the Google stack frame, which represents the page that you're currently on. Same thing goes if you have a mobile phone. I think Android and iOS both have it, where there's a back button in the bottom left. Whenever you click on a new page, it opens that up, adds it to a navigation stack. Whenever you hit back, it pops it and goes back to the last one. And we also said that the stack is used for calling functions. So if I had a function called foo, and a function called bar, which calls foo, and then we have main, and main calls foo, and then main calls bar. It will keep track of a stack here. The bottom frame of the stack will have main. Then when it goes to execute this, foo gets executed, which means it jumps over to here. Anytime you call a function, it will add a stack frame for it. Whenever you return from that function, so after foo is done executing, the place it should jump back to is over here. We remove it, and the new top of the stack is where that function, or what function is currently being executed. So after foo finishes the first time, it will return back to main. Then it will pick up where it left off, go to this next line of code, which is bar. Bar gets added to the stack, and then bar calls foo. So foo gets added to the stack on top, and then after foo finishes executing, we go back to where it was called, which is right here in the bar function, not in main. Notice that they both call foo, but the one that we will return to this time is the one in bar. After bar finishes, it returns to main, and then once main finishes, it gets popped from the stack, and when nothing is left in the stack, you know the program is done. So this is done because we want to keep track of the order that functions were called in. We need to keep track of their history as well as their order. And notice that foo in particular gets called in multiple places, and so we need this because we need to know where to return back to. Do we return back to main? Do we return back to bar? It depends on who called it at that given moment that we're executing the program. So you have this call stack. which is responsible for maintaining function calls. And this is why, if you remember, you get stack overflow when doing recursion, is that you maybe have too many function calls, the stack gets too big and it overflows, which is just an overflow is when the stack runs out of space, or when one of those frames, one of those blocks that we were creating is too big, it might also overflow. But generally, I would say understand how a stack works, remember what push and pop do, and how these data structures function, maybe some general applications of them, right, is what we want. And I think that about does it. So this is the last review session. If you have any questions, please reach out to me via email. I'll be happy to talk about anything if you're confused on any topic, and I wish you the best of luck.